Hi, everyone. Welcome back to another Talk Math with your friends. Today, our speaker is Dr. Jacoby. She is an independent mathematician, the owner of Jacoby Consulting, and the host of the Art of Mathematics podcast. Today, she will be telling us about the Barber Paradox and foundations of mathematics. So please join me in welcoming Dr. Jacoby.
Thank you, Tian. I hope everybody can hear me. There's a very loud leaf blower outside. It's okay?
No problem
Okay,
from
good.
here.
All right. Let me share my screen. Okay, give me a thumbs up if you can see the Barber Paradox. Okay, thank you. All right. I'm going to be talking about some things where we can really fall down some rabbit holes. So what I would prefer is I'm going to ask you some things because I want everybody to be engaged. But at the same time, I'd like you to hold any questions or any deep questions or discussion for the end. Is that okay?
Sure.
Okay, what I'm going to be talking about is something that looks like just a riddle or a joke, some of these paradoxes, and show how they really shook the foundations of mathematics. This talk should be accessible to anybody who's familiar with just basic sets and proofs. And I'm going to start off giving you a quiz, but it's just one question and it's multiple choice. So put your answers in the chat box, which I can no longer see. I'm not seeing the chat box. That's I can see up here.
So we've got E, F, E factorial, C, B. I want a superposition of A, B, and D. Gamma of pi.
So what happens here? Anybody want to talk about it?
Well, there's two 25s. So if the answer, like usually you think of it at 25% to guess the right letter, but because the answer is duplicated, you think it's 50%. But then there's only actually a 25% chance that you pick the 50%.
Right.
And so it's sort of this circular, like I can't, yeah, as TJ put out, it's self-referential.
Yeah, and self-referential is what this whole thing's about. So this is just an example of the twisty mess your brain can get in with some of these paradoxes. This happened to be stuck up on a bulletin board in Caltech, so that's a clue. Now this came from this guy, Epimenides, like a couple thousand years ago, who was from Crete, and he said all Cretans are liars. So you've got a paradox there, ostensibly. If he's telling the truth, he says he's a liar, so he's lying. And if he's lying, then what he's saying isn't true. And then he's telling the truth. Anybody see the flaw in this simplistic argument here? Is there a fix to this particular one? By the way, for some reason, I can't see the chat now, so I'm going to have to ask people to talk. Anybody see the flaw?
What's a liar?
Yeah, what's a liar? Yeah. Yeah, and can you elaborate on that?
He could be a liar. Could be defined to be somebody tells a lie at least once.
Yeah, right.
All
right.
the time.
Yeah, yeah. So it could be the case that when he says all Cretans are liars, he may be telling the truth because they all lie part of the time, and that's okay for him to be telling the truth now, or he could be lying, and it's not the case that all Cretans are liars because there's this one guy who's not a liar. And there are all these exceptions. So let's get rid of all that falderall and get it down to the essence. the essence of this paradox is just what I'm saying now is a lie. That statement talking about itself. And that's the basis of all these paradoxes. And you'll see a lot of variations on it. Here's Epimenides' t-shirt. And can you imagine what it says on the other side?
Statement on the front. This t-shirt is false.
Yeah.
Yeah.
The statement on the
Oh,
front
true.
of the shirt
Sorry.
is true. Okay. So you work that around and oh, well. And again, you get a paradox where if it's true, it's false. If it's false, it's true. And you can get even more complicated. Alice says what Bob says is false, and everybody's saying what the next person says is false. And if you believe Alice, then you don't believe Bob, which says you believe Chris, which says you don't believe Alice. You can start anywhere and go through these loops. There are all sorts of examples like this, and I'm just giving you a little taste of some of these twisty paradoxes. And they're kind of fun. One solution that people offered is throw out the law of the excluded middle. You don't have everything as either true or false. There may be some things that are neither true nor false, but you still have the paradox that says this sentence is not true. And you've got the same paradox there. Well, if it's true, then it's not true. And if it's not true, then it is true. So what does this have to do with math? It all started around the turn of the 20th century. Mathematicians started getting concerned about what's math built on? What are the foundations? It looks solid, but what's holding it up? I mean, is it just like this building looks solid, but there's a bunch of old tires holding it up? What's underneath all of math? And is it strong? And can we prove it's strong? Or are we being misled by some sort of preconceived ideas? Like you're thinking about geometry. Oh, I know what a parallel line looks like. And so you come up with these ideas based on an image that you have in your mind, and they may not follow logically from other things. And they're the two areas that I'm going to be talking about. One is set theory, and the other is the axiomatic method for proving things are true. Now, set theory is pretty simple. They teach it to kids. I don't know about you, but when I was in college, it seemed like every math book, no matter what it was about, started off with set theory. And I'd say, oh, differential equations. Oh, this is easy. It starts with set theory. I know this stuff. And the kids do it, and they're taking Venn diagrams and all that. So this is pretty fundamental stuff. It's just collections of things. And that was the original definition of it, what they call naive set theory now. Any well-defined collection, anything that you can say, a collection, the collection of all things that have a certain property, as long as it's a pretty definitive property, like all the living people in the world at a particular time, or the set of all prime numbers, or even the set of all even integers that are not the sum of two primes. Well, we don't know what's in that. We can test it. It's a testable question. We can test the 2 is in it. It's even, it's not the sum of two primes. 8 is not in it because it's 3 plus 5, but that's Goldbach's conjecture. We don't know whether there is anything else in there besides 2. But you can still talk about that as a set, even though you don't know exactly what's in it. Now, one thing you could put in a set is a set of sets. You can put other sets in a set. It seems kind of crazy, but it turns out it's legal. And not only that, it turned out to be really powerful. And you can build up mathematics this way. You can define 0 to be the empty set, and you just start with the empty set, and you start making other sets of the empty set and sets of sets, and pretty soon you've got all the integers. And then you can come up with, or you can define ordered pairs, you can mod out by stuff, you can get Dedekind cuts and get the reals. all this is built on nothing. It's all built on the empty set and just the concept of sets. So this is really a powerful thing that we want to hang on to. But then the question is, can a set be an element of itself? Well, no. I mean, your first thought is no. You think of the kind of sets we talk about. The set of even numbers isn't an even number. The set of puppies or whatever it is kids study is not a puppy. But some sets can be. These are kind of weird sets. We'll call those abnormal sets. So normally the sets we see are not elements of themselves. Can anybody give me some examples of an abnormal set?
The set that contains only itself as an element,
Okay, is there such a thing?
depending on your axioms, yeah.
Yeah, yeah.
Fine atoms.
That's right. That's right. We haven't said you can't do that. Any others?
It's not really a set, but a community of communities is itself a community
Yeah.
sometimes.
Uh-huh. Yeah. Let's see, I had some here. Like the set of all abstract concepts is an abstract concept. Of course, the set of all sets is a set. Or the set of all things that can be described in 12 words, which I just described in 12 words. There's a little problem with that one that we'll get to. Okay, so Bertrand Russell came around, and he came up with this paradox. He said, if you take the set R of all normal sets, and remember, those are the ones that are not members of themselves, which is kind of what you'd expect. Is R an element of R? Very simple question, very simple set. It's defined by a clear description. And then the question is R an element of R? And if it is, it's not. And if it's not, it is. And this seems like kind of a little joke, but it's a contradiction in set theory, in naive set theory. And once you get a contradiction in mathematics, the whole thing collapses. It's like that house on the tires. You pull out one of the tires and the whole thing falls apart, because now you can prove anything. So at that point, everybody realized, wow, set theory needs a much more rigorous foundation. Now I've got to mention the Barber Paradox, because everybody always mentions that in relation to Russell's paradox. This was not original with Russell. People seem to think that this is what inspired him, but he even said it wasn't a very good analogy, and I don't either. Okay, the town barber shaves everyone who does not shave himself. Who shaves the barber? Well, if the barber shaves himself, oh, then he shaves himself and he's also shaved by the barber. Or if he doesn't shave himself, then the barber doesn't shave, So we have a paradox ostensibly, but can somebody give me an example of a way you can get around this paradox?
People with other pronouns.
Yeah. The barber is a woman, right? What else?
It doesn't actually say that he only shaves the people who do not shave themselves.
That's right.
He could shave other people.
Yeah, that's right. It doesn't say that. He could shave himself and he could, and the barber could shave him both. It doesn't preclude that. So you've got to say he shaves everyone and exactly those who do not shave themselves. And then you also say the universe is men who don't have full beards, and it gets into this big thing. Whereas you go back to Russell's paradox, it's very clear. R is exactly the set of all normal sets. You don't need all this other falderall to explain it. It's very clear and very concise and very clearly a paradox. So what happened from that? I mean, everybody's suddenly set theory, which seems so solid and the basis of everything, everybody's going around saying, well, now what do we do? And there were actually three things that happened. One is they modified or came up with axioms for set theory that would preclude this happening. And recently, I think this was 1988, there's a theory of hypersets. And somebody mentioned the set whose only element is itself. And that's the kind of thing you can do in this theory. So that's really mind twisting. But the main thing was the axioms, Zermelo-Fraenkel axioms. And this one right here, the axiom of regularity, implies that no set can be a member of itself. So the set of all sets goes away, Russell's paradox goes away, all sets are normal. And you can only talk about sets having a particular property like that number 3 if they're within a set that you've already defined to be a set. You can't just say this, the collection of all things everywhere. It's got to be within a set, and then it all works out. Okay, here's the rest of the axioms. There's in the chat is a link to the slides. So you can look at these later if you want. And then this is the recent work that's really mind-bending, where you've got non-well-founded sets. This book, The Liar, is probably the easiest read and also has a lot of interesting things about the liar's paradox, really crazy versions of the liar's paradox. And there's a set that is equal to its own, the set of itself. So I'm not going to go into that, but the other thing that happened was looking at how can we build it from axioms? How can we come up with basic truths or basic assumptions or whatever you want to call them that are going to give you all of mathematics? And the granddaddy of this kind of thing, of course, is Euclid's axioms. They're the 5 axioms. And this is what got me interested in math in the very first place. That there are these 5 axioms, and if you accept those, you can prove all sorts of crazy things. You can get all of plane geometry just out of your head. Now, later they realized, well, that 5th one, well, you could change that and you could get a completely different geometry. Peano's postulates for finite cardinals. It's another example. But what they wanted to do, and Hilbert put this down, I think this is the second problem, is to come up with a mathematical theory of everything. And this, at that time, around the turn of the 20th century, just became the holy grail of foundational mathematics. To try to find a finite set of axioms from which you can derive all of mathematics. Furthermore, these need to be consistent. You don't want them to be contradicting themselves. And you need to prove that they're consistent. So this was the goal, was to come up with a way of mechanizing all of mathematics. And Whitehead and Russell, Alfred North Whitehead and Bertrand Russell, got together and over many, many years and many struggles, produced this 3-volume book, Principia Mathematica, the principles of mathematics. And this is, the goal of this was to do exactly this. And this is what a page of it looks like. It's all symbols. The idea here is to turn it all into essentially meaningless symbols. Now they all relate to something, but it's intended to be a game where you just take symbols and take rules and run it through and see what the consequences are that fall out. So it's all very mechanistic. The reason is we want to get completely away from any preconceived notions that are driving what we think of as truth. Well, and they worked on that for a long time. And then in 1931, the mathematical theory of everything got shot down. Kurt Gödel, he was 25 years old. He just finished his doctorate. And he announced his first incompleteness theorem. And it says, this isn't going to work. No matter what you do, this plan isn't going to work. No matter what your axiomatic system is, if it's consistent, it's not going to be enough to prove all the true statements of arithmetic. And John von Neumann happened to be in the audience, and he immediately understood the implications of this. And he said, it's all over. Later, Hilbert learned about it, that his whole idea, his goal was impossible. And he and Bertrand Russell came to terms with it and said, the mathematics is solid. And so this is what it is what it is. So what I want to talk about is how did Gödel prove this? Essentially, it was a mathematical statement, just like the liar in English, which says a statement that says, I am not true. Gödel came up with a statement of math that said, I am not provable. And the question is, well, how do you get a mathematical statement to talk about itself? That was the real trick. Well, here's another paradox, an analogous one. You take all the properties of numbers and you write them out in words or symbols and put them in some predefined order. It might be you start with the smallest number of words or letters first and do those in alphabetical order and keep going and get some kind of order. So it might look like number 1 might be is even, number 2 is prime. And then you define, you say a number is Richardian if it doesn't have its corresponding property. So in this particular list, 1 is not even. So 1 is Richardian and 2 is prime. So 2 is not Richardian because it does have the property of being prime. And somewhere in that list, you've got a property of numbers called is Richardian. And let's call that M. So the whole question is M Richardian? And you run into the same thing you did before. If it is, it isn't. And if it isn't, it is. Now, the solution to the paradox, anybody have any idea on this one? This is a lot more subtle than the other ones, and it's key to Gödel's proof.
You haven't told us how you listed all the properties. So if you can't actually list all the properties like that, that's going to be, then this doesn't work.
Yeah, that's right. It depends on how you list the properties, and maybe you can't. Maybe you can't. But I think you could. You could say, take a particular list of primary words, or you could do it completely in mathematics. You have multiplication and addition and the numbers and so on. Okay, so it's a limited language. So there's going to be, for every number, you'll have a string of that size. And you write all those that make sense by the syntax. And then you go to the next number and write all those. So I think you could make such a list.
So the question in the chat is whether or not this collection of properties is countable. In which case, if it's not, you wouldn't be able to.
Right, yeah. I think it is countable if you start off with a finite number of symbols. And you can do that. We'll see that in a minute, where you can take the successor of 0, and 1 is the successor of 0, and 2 is the successor of the successor of 0, and so on. So you could start with a finite number of symbols and make statements of mathematics, and you could come up with a countable list. I wish I could figure out how to see the chat. Let me try something here.
If you
On your
click on
green share, there should be a chat button. It'll pop up as a separate box.
on the share. Oh, okay, here we go. There it is. Thank you. Okay, well, that'll help.
Mhm.
Logic comics, yes. Okay, now I got to go back and read these. Are the properties countable? Yeah, okay.
What's
Yeah,
property?
pardon?
Oh, I was just reading.
Okay,
So Drew
yeah.
asked, what's a property? Is it a subset of the natural numbers?
Yeah,
Doug asked, is unprovable, like the continuum
is-
hypothesis?
yeah, that's getting into, yeah, what is a property? And that, I think that gets into it. Richardian, is that a property of numbers?
Mhm.
And it's a property of these strings. So it's a distinction between mathematics and metamathematics. And this is at the heart of all that.
Then Kim asks, does it matter if we can or can't check the property in a finite amount of time?
I don't think it does. I think this assumes that yeah, that's a good question. We're getting into a lot of good questions that I didn't even think of. Yeah, there's a whole bunch of issues with it, aren't there?
Mhm.
The issue that I was thinking about that's really at the heart of all this is it's a distinction between mathematics and metamathematics. That the property of being Richardian has to do with the symbols. And that's metamathematics, which is looking at symbols. Mathematics is looking at the numbers themselves, properties of the numbers. Metamathematics is looking at numerals. So for example, in mathematics, you'd say 5 is larger than 3. But in metamathematics, if you write 3 large enough, then 3 is larger than 5 because it's talking about symbols. I think that's a good example of the difference between numbers and numerals. Or you could make a statement like 2 + 2 = 4. It's a statement of mathematics, but if you say that statement contains 5 symbols, that's metamathematics, or something's an existential formula. So we're talking about statements about numbers rather than statements about symbols. And the Richardian is actually a statement about the symbols. It's a statement of metamathematics. So the question comes up, how is Gödel going to be able to do this? How is he going to be able to bridge that divide between mathematics and metamathematics? And here's his insight. You looked at that page from Principia Mathematica, and it's all symbols. There's no words at all, it's just symbols. And Gödel said, well, why don't we just change these into numbers? And then it's just a matter of not just symbol crunching, it's number crunching. And you can take the symbols and translate each symbol into a number. And then you can translate a string of symbols into a number. You can translate a string of statements into a number. And there you have a proof. There's a proof and as a number. And so you've got numbers that are talking about numbers. And you can have numbers talking about themselves. So now you're getting into this twisting around, numbers talking about themselves and math talking about itself. Now, how can this be? Principia Mathematica worked on for years and years, developing this theory of types that was rigidly hierarchical. So you can't have things that go back up. You go down into the sets, you've got subsets and subsets and subsets. you can't have something loop around itself. It was distinctly built to do that. And here's what he did. He assigned a number to each one of the symbols. A finite, what I was talking about before, you have a finite number of symbols with which you can express statements of mathematics. And then you've got some others for the variables. So with this language, you can write anything in anything in number theory. We're talking about number, we're just talking about the natural numbers here. But that still is pretty rich. This gets into a lot of unsolved problems. And you take, for example, a simple statement like 1 + 1 = 2. Well, there isn't a 1 or a 2 in this list of symbols, but there's a 0 and there's a successor of 0 that gives you 1, and a successor of the successor of 0 gives you 2. So you can write that out, and then you can take the numbers and say, okay, that corresponds to this string of numbers, 7, 6, 11, blah, 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 blah. And then Gödel's trick was, I'm going to put all that not as a string of numbers, but as a single number. And using the primes and powers of primes, you put it together and you come up with this horrendous number. But still, it's just a single number. And then once you do that, you can actually do metamathematics in mathematics. So here's an example of a metamathematical statement that says the first symbol in a particular formula is the tilde, representing negative. Okay, that's a metamathematical statement. It's talking about the symbols in the formula. And the way you do that is you see whether the first symbol is a tilde, which is going to be, the first one is always the power of 2. And you want it to be a 1, which is the number for a tilde. So if it's divisible by 2, but not by 2 squared, then the first number is the tilde. Very simple example, but a very powerful way of doing it, of actually having a metamathematical question answered mathematically. And so he expanded on this. He gave Gödel numbers to formulas and to lists of formulas and rules of inference. All of those could be written mathematically. And what's a theorem? It's just a list of formulas where each one follows from a previous one, or it's an axiom. And so that's something you could write an equation to test. And again, it's all in math now. It's just arithmetical checking. So you come up with a statement of arithmetic that says the sequence of formulas with Gödel number X is a proof of the formula Y. Now, one thing that Gödel did that really validated Principia Mathematica is he proved that all the true primitive recursive statements of arithmetic, and there's a lot of them, I mean, those are the key things of arithmetic, are all theorems, can all be proved within Principia Mathematica, within that structure. So it really validates it. And the other thing is, all the theorems of Principia Mathematica are actually true statements of arithmetic. So that's very powerful. But on the other hand, he was able to say,
wait, what does that mean? What does that last phrase mean?
it says if you have, yeah,
Oh, okay. I'll talk to you
if you have a theorem, you prove some theorem in Principia Mathematica and get a statement, you take that statement in symbols and translate it back to arithmetic, it's going to be a true statement about numbers.
Like our casual knowledge of the natural numbers from school? Or do you mean when you convert it into his Gödel numbering that there's whatever arithmetic thing there.
No, as an actual, so if you prove, say, Goldbach's conjecture in Principia Mathematica, if you could do that, then this proves that that would actually be a true statement of number theory.
Okay, I'm suspicious, but go on. Because I don't, is there some other set of axioms for number theory that's relative to? Because without that, I don't know what that sentence means. But that's fine, go on.
Well, the true statements of arithmetic, I'm not talking about proving them, okay? You prove it within this particular context with the axioms that they have there that they're using. And I don't understand Principia Mathematica, so I'm not going to speak to that. But if you could prove something in there and then translate that, not in completely independent of Gödel numbers, but just translate it into a statement of arithmetic, which is a statement about numbers and is either true or false, that statement will be true. Not that you
Okay.
can prove it in any system, but it will
Sure.
be a true statement about numbers.
But is that just that the axioms of Principia Mathematica are a subset of the axioms of arithmetic? Or is there something else going on there?
I assume, yeah, they include the axioms of arithmetic.
Maybe I had it backwards. Yeah, sure.
Yeah.
No, maybe it's the other way. All right, continue. Thank you.
Yeah, thanks. Okay, so now the steps that he goes through, you can take a formula, you can give it a Gödel number. You can take a bunch of formulas, you put those all together, you get a Gödel number. You can take any statement. If you take a statement about formulas, that turns out to be a statement of arithmetic. Like we just talked about, the first symbol in this formula is a negation sign. Okay, this statement is a negation. That's a meta-mathematical formula. And you can turn that into an arithmetic formula. And one of the things you can do is you can say that list of formulas is a proof, because you can codify all of the ways that you can do inference from one to the other. It's really messy, and you don't want to do this. You don't want to be messing with Gödel numbers. But he proved that this can all be done, and it can all come out as statements of arithmetic. And in particular, you can say the sequence of formulas with Gödel number X is a proof of the formula with Gödel number Z. And one thing he proved was that if it's a primitive recursive relationship, then it's a statement in Principia Mathematica. And that means if that's true, then you can prove it. So now we're going to go, again, this feels like feeding the snake its own tail, and that's what we're going to do. So you start off with a formula that has a variable in it. It's a free variable called y. And you can take its Gödel number, and then you can substitute that number in the original formula in place of y. So you've got now a formula that's talking about itself, which seems really strange, but that's the key to this whole thing. And in particular, you can come up with something that says, this statement is not provable. So you've got a statement that's talking about itself, saying, I am not provable. And that's a statement of meta-mathematics, but you can say it in arithmetic. So here you have the statement G, and it says G is not provable. So the question is, well, is it provable? Again, it's provable if and only if it's not provable. And you get a contradiction. You also get a contradiction if you say, is not G provable? You can't prove either G or the negation of G. So here's a statement that cannot be decided. Furthermore, it's true because what it states is it's not provable. And we've taken this meta-mathematical argument to say it's not provable. And so the conclusion is that if you take Principia Mathematica and it's consistent, there will be true statements, in fact, infinitely many of them, that can't be proved or disproved within the system. The system is incomplete. And not only that, even if you add that statement back in, there's going to be some other statement that you can't prove or disprove, either way. So in general, no matter how rich your axiomatic system is, finite axiomatic system, it can't produce the whole truth and nothing but the truth. Even if you focus only on arithmetic, they're trying to do this for all of mathematics. They can't even do this for the natural numbers. So at that, John Neumann said, it's all over. But it wasn't, because it was kind of interesting for him. He and Turing went off and said, well, let's see what we can prove, what we can get out of this mechanistic approach, and essentially started computer science. So here are the implications. The bad news is Hilbert's program is dead. Math can't be mechanized. The good news is math can't be mechanized. We are not machines. There's still some art left in mathematics.
Or we're deluding ourselves.
Or we're, yeah, I don't know. And now my question, I'd like to open it up to everyone. What do you think? Is this good or bad? Or what exactly does Gödel's theorem mean for us?
Yeah, we can clap. Really, and then let's have some discussion.
Yeah.
So Cameron, I know you probably have some thoughts.
Gödel's theorems are great news because there's a lot of beautiful math that has come out of this like hierarchy of what different systems can prove with stronger systems. Anything that lets you do a lot of beautiful math is good news in my view.
Yeah, thank you.
I really loved Rebecca Goldstein's book, Kurt Gödel, the Incompleteness, the Proof and Paradox of Kurt Gödel, which is where I learned a lot of these ideas. And her thesis there is that Gödel and Einstein both had very strong sort of like philosophical feelings about the implications of their results that were at odds with the sort of way it's used in sort of in pop science, which I think is really, really cool. I certainly love the talking about incompleteness with my students, because they often believe that like math is the one place where everything is knowable in exactly this way, and I'm just like, no. I sort of say like maybe it's a human endeavor where the direction I go from this stuff is like, so the question isn't whether or not it's true, it's what we can know as people.
Yeah.
So.
Let's see, I noticed somewhere in the chat, somebody mentioned Logic Comics, which is a great book.
Yeah.
If you want to know about the
That's it.
history of this, it's a fun read, and it's also a self-referential book about self-reference, which I think is wonderful. And that's what all this twisty stuff is about. It's all self-reference.
Yeah.
Yeah, there you go. Yeah,
Cameron and I both have our copies.
yeah.
I
I've read
actually,
it. Pardon?
I made a mistake in my reference earlier. I like being wrong. I was referring to a book like it's another book of that type of genre, but actually there was a mall in it, and in the mall there were many shops, but there were places like the Yang and Mills Emporium and a lot of other places like that. And there's actually Terry Towers drawn as a cop, as is Ben Green. But anyway, sorry, I
Yeah, I
digress.
know. Prime Suspects.
That's it.
Yeah,
the one.
yeah.
It's great fun, but it was like, sorry, I mixed up my books.
Yeah.
Sorry.
Who would have thought there are two graphic novels about math?
I'm sure there's a third that nobody's read yet.
Yeah.
Hopefully there are hundreds in the works.
Yeah, I just put in the chat my contact information. Let's see, and the slides, which is a repetition, and recommended books, all the books links, Amazon links for all the books I mentioned. So another one, of course, is Gödel Escher Bach, which is another wonderful self-referential book on self-reference and about Zen and artificial intelligence and Alice in Wonderland, and very witty, wonderful book. And if you really want to get into Gödel's proof, there's Nagel and Newman's book. So I recommend all those.
Great.
Okay, I'm sorry. Let's see. Were there any unanswered comments or questions from the chat?
Well, I had no, I don't think so. Well, I mean, there were some, Kim asks, will there ever be not artificial examples? I don't know exactly what that was a reference to. But I had sort of a broader question. When you sort of kept saying, like, prove all of mathematics.
Yeah.
And I don't know what that means. And it feels very Platonic, right? You sort of have to assume this body exists out there.
Yes.
And, so I don't know. I just sort of like, I was wondering if Platonism was in there even more than I noticed before, or if that was just a turn of phrase.
I think it's there. The impression that I get is that was the underlying assumption, was that mathematical truth exists out there and it's for us to find. And so we're going to build this machine that will help us find it. Let's see.
So I have a question.
Sure.
So you don't like the Barber Paradox. Is it possible to have, a kind of more popular culture version of the paradox that would be, closer to the right thing?
The way they described it, they talked about the Barber Paradox in Logic Comics, and it got kind of convoluted, where they were talking about, in this town, there was a law that required all men to shave, and it required all men to either shave themselves or to have this particular barber shave them or something like that. And it just seemed to be really convoluted. The simplest one that I can think of is just the pure liar paradox. This statement is false. But I can't think of any clean way to do the Barber paradox.
The problem is if the barber doesn't shave,
Right. Yeah.
okay, and then goes off to sell coffee. No, sorry, and then goes down that particular road. There's like, they're not shaving, so they're not complying with the law. And yeah, clean shaven mathematics needs coffee. Thanks, Kim.
Yeah.
it doesn't seem that it opens itself to simplification. If you want to think about it, like who's going to, it refers back to the barber. Who's going to shave the barber? Maybe the barber isn't from that town, so therefore the barber doesn't have to shave or can shave themselves. But I don't see anything else in there.
You don't see that it's a paradox, you mean?
Oh no, I see that. I see that. But trying to escape it being a paradox, trying to codify some kind of way to not have it be a paradox, seems to me very, as you said, convoluted. It's like the way they do it in the book.
Yeah.
That's different. They're trying to demonstrate that it is a paradox.
Right. Yeah.
I'm tying myself up into knots verbally.
Yeah, it seems like to make it a tight paradox, you have to be very, very precise. And then it kind of loses its common man feel.
Joseph has a nice question.
Yes.
To which I'm sure you know an answer. Are there examples of statements that have been proven to be unprovable?
The continuum hypothesis.
Meaning that there's a size of infinity between the size of the natural numbers and the size of the real numbers.
Yes.
That's independent of the rest of set theory. And Gödel, in fact, was one that proved half of that, right?
Yeah, he proved, what did he, no, I can't remember which half he proved. And Paul Cohen proved the other half. Yeah, that they're both consistent with the mathematics with the basic mathematics.
Consistency of the continuum hypothesis, and Cohen wrote independence of the continuum hypothesis.
Okay, thank you.
Thanks. Do any of you think the Riemann hypothesis is unprovable? Or is that too much of a flashpoint to ask a group of mathematicians?
Yeah.
Talking about the liar's paradox always reminds me of sort of the opposite one, which is also problematically sexist, the traveling salesman who comes to a town and says at least one of you, everyone knows everyone else's spouse is cheating, but doesn't know about their own, and the salesman comes in and says that one of you is cheating, one of your spouses is cheating, and once that information is public, then when nobody gets kicked out on their doorstep that night, that means everybody knew about somebody else, but it wasn't theirs. So that means the next day everybody knows about two of them. And then so it sort of iteratively cycles where the knowledge, the meta knowledge becomes knowledge in each iteration. And then inductively after a certain number of times of cycles, everyone knows that everyone else had to have known that their spouse was cheating, and therefore so that it's true. And so to Moira's question before, I tried really hard to rewrite that in a way that wasn't so that didn't involve so much not horrible sexist nonsense. And
okay, I've got one.
It was really hard, and the sort of this distinction, yeah. So and then there's the sort of like exoticism version that is a little bit complicated, but I think there's the distinction between descriptive truths and universal sort of statements. And so I think you have to go into the world of law or games or something like that in order to have this paradox in a clean way. I don't think you can have it in the casual way that doesn't have the problems you were concerned with, Carol.
Yeah, probably not. But I do have one for you for the problem that you were just talking about with the unfaithful spouses. Is the dirty children. Let's see if I remember how this goes. The logician sees his 3 children, they've been playing in the mud. And he says, and they're all very good logicians, of course. And they can see each other, but they can't see themselves. And he says,
at least one of you is dirty.
At least one of you has a dirty face. do you know whether you have a dirty face? And they look at the others and they go, no. And then he asks again and they go, no. And then he asks the same question again and they all go, yes. So I think that's the same paradox
Same
you're
puzzle.
talking about. Yeah, that's the
But
same
you've got to
puzzle.
like brute force in this like cycles where they publicly communicate. And when I've tried to do this, they were like, you know, a very reasonable person would like touch their face rather than wait 3 cycles to use logic. Like it's real hard to get a version of this thing that doesn't feel artificial.
Yeah, that's true. That's true.
In my version, there was like an edict from a god, which is the same thing. So artificial.
Yeah.
There's a puzzle like that with red and green hats.
Mm-hmm.
There are people standing in a line and each person has they put on their hats in the dark. And then each person can see all the people in front of them. And the idea is to tell whether you have a red hat on.
Mm-hmm. I agree. Very similar feel. Great. Well, we're almost out of time, so I'll just wrap this up and say we have I believe, 2-week hiatus. We're taking a little spring break as everyone finishes their grades and is exhausted and catches their breath and things like that. And we will be back on, I believe, the 27th. Drew, do you remember who our presenter is for that one? I don't remember.
Isn't it Brendan? Is Brendan still here?
Oh yeah, it's Brendan. Are you here, Brendan?
Yeah, I'm here.
Great. You want to give us a 30-second preview?
Sure. So I'll be going back to sort of like what was last week, some graph theory and some sage coding as well. I'm going to be talking about the cops and robber game on graphs. And part of my talk is I'm going to propose that we call it chaser and runner, just because it preserves the C and the R, and I'd rather not talk about cops if I don't need to. And so I'm going to be talking about some products, graph products, the Cartesian and strong product. I'm going to use those to create some interesting graphs on which we can play the game, and then show you some algorithms, some code that I have that can calculate various things about this game. And so throughout the whole thing, it's going to be kind of a big call for collaborators, and I'm going to have a ton of open problems and conjectures. And so I hope to get everybody interested in solving these kind of puzzle problems that I've been working on.
Excellent. Well, please join me in so everyone should come back in 3 weeks after a 2-week hiatus for Brennan, and then please join me in thanking Carol for today's session.
Thank you, everybody.